If the system absorbs heat, its temperature goes up, right? Temperature is the measure of the thermal energy of the system. It's going to increase by delta T. Delta T is the change in temperature. The change in temperature is directly proportional to the amount of heat absorbed. You put in twice as much heat, the temperature will change twice as much. And the proportionality constant for that is called heat capacity. And that is, has the symbol capital C. The units of heat capacity are joules per degree Celsius or joules per Kelvin. Now remember that degrees Celsius and kelvins, the units are the same size. And here we're talking about a change in temperature. So whether you measure it in Celsius or Kelvin, the change is the same. Okay? So the change is the same. So Q, the heat, is equal to the heat capacity times the change in temperature. Heat capacity is defined as the heat required to change the temperature of a system by 1 degree Celsius. There are different factors that affect heat capacity. If you have an object with a larger heat capacity, let's go back to that equation. If you have a large C, where am I going with this? Smaller temperature, yeah. So let's just rearrange this and look at it. So the change in temperature is something that we can measure. The change in temperature would equal Q divided by the heat capacity. If you have a fixed amount of energy that you're putting into this object, the larger C is, the smaller the change in temperature. If C is very small, it's going to heat up more. Does that make sense? Some things heat up faster than other things. And when something heats up, it absorbs energy. When it cools down, it releases energy. Have you ever noticed that, like, if you go to maybe a steakhouse or something and you've got a baked potato and a steak and maybe some Texas toast, and it all comes out hot, does it all cool down at the same rate? No. What stays hot forever? That darn potato. Why does the toast cool down so fast and the potato doesn't? Weight has a little bit to do with it. Most of it's heat capacity, though. Heat capacity. So, large heat capacity, you're going to have a smaller change in temperature. Small heat capacity, you'll get a larger change in temperature. Heat capacity would be an intrinsic property. So the heat capacity itself does depend on the amount of matter. Well, okay, so I just lied to you. There's heat capacity and there's specific heat capacity. Heat capacity is extensive. Specific heat capacity is intrinsic. Because specific heat capacity accounts for, it brings a mass term into there. So specific heat capacity is going to be joules per gram degree Celsius. Whereas heat capacity, which is a not useful quantity at all, is going to depend on the amount of stuff. So specific heat capacity is the amount of heat needed to raise the temperature of 1 gram. And so that's what makes it an intrinsic property. It's not going to depend on the size of the object because it's per gram. And so the units of this will be joules per gram degree Celsius instead of joules per degree Celsius or joules per Kelvin. And sometimes we use the molar heat capacity, which would be the amount of heat needed to raise the temperature of 1 mole of a substance by 1 degree Celsius. And then it will have units of joules per mole degree Celsius. And because both of these incorporate the amount of matter, they are intensive properties. So we can quantify heat energy in this way. Q equals mc delta T, where this is the specific heat capacity. So this is an equation that you need to memorize. So there's a test called the MCAT. Have you heard of that? Yeah. Does that kind of look like MCAT?
Yes.
Yeah. So sometimes I call this MCAT. Q equals MCAT. The delta kind of looks like a capital A. MC delta T. So we can do all kinds of fun problems with this. Of course, fun is subject to interpretation. A 55.0 gram aluminum block, initially at 27.5 degrees Celsius, absorbs 725 joules of heat. What's the final temperature of the aluminum? Well, we can use this equation to figure that out. 725 joules of heat, that's Q. So Q equals 725 joules. Q equals M. What's M? M is the mass. They give us the mass. I'm writing with my finger today because I broke my stylus. No, my children broke my stylus. 55 grams. Could be worse. They could have broken my iPad. That would be worse. 55 grams is the mass. What's the specific heat? We need to look it up in a table. You don't need to memorize those things, but you need to be able to think, oh, I need to go look for that. So this is aluminum. Here is aluminum 0.903. And these units, important to always have your units. CS that's the specific heat capacity, 903 joules per gram times degrees Celsius. Now, this temperature, is that the delta temperature? Is that the change in temperature? No. It's initially at this temperature. So that must be the initial temperature, right? Well, let's put that up here. This is not a well thought out slide. So the initial temperature is 27.5 degrees Celsius. They want the final temperature. We have Q, M, and C. What would be easy to calculate using this equation? Delta T, right? So we can rearrange this equation. We'll divide this side by M and C, and we'll divide the other side by M and C. And then we come up with delta T equals Q over MCS. So delta T, Q is 725 joules, divided by the mass, which is 55.0 grams, times the specific heat capacity, 0.903 joules per gram degrees Celsius. Joules cancel, grams cancel. I forgot to get my calculator out. At least I brought it. 725 divided by 55 divided by 0.903, 14.5978 degrees Celsius. How many sig figs should that have? 3. That's the change in temperature. So a positive change in temperature, it's a change in temperature, sorry. Let's try that again. The change in temperature, did this piece of aluminum, did it get warmer or colder? Warmer. The change in temperature was positive. The temperature went up. So if this is the change in temperature and this is the initial temperature, how do we find the final temperature? we add them together. So we've got the initial temperature of 27.5 degrees Celsius, and we're adding the change, blah, 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 7 and 9 and 1 and 12. Did I do that right? Where's the uncertain digit in this 42.097? It's the 0. Because this temperature was to the nearest tenths place, and so this will also be to the nearest tenths. This one was to the nearest tenths as well, and so they all just kind of lined up really nice. And so the final temperature is equal to 42.1 degrees Celsius. Any questions? You should have seen calculations like this in your previous chemistry class. Water actually has a very high specific heat capacity. It can absorb a lot of heat without changing its temperature very much at all. And water has a big impact on our climate. If you've ever gone to the coast, you know that the temperature variation there is much less than the temperature variation that we have here. Here we can easily have a 40-degree temperature change from the low at night to the high during the day. At the coast, it's probably more like 10, 15 degrees because you've got this huge body of water there. And the sun is bringing energy in, and the water absorbs the energy, and its temperature goes up very, very slowly. And then at night, when the sun is on the other side of the planet and everything cools down, the water is releasing energy and slowly cooling down. And so it moderates the temperature. We use water as a coolant because it can absorb a lot of heat. So the radiator in your car has water in it. It circulates through the engine, the hot parts of your engine, and absorbs a lot of energy without changing its temperature as much as many other fluids would. And then it comes around to the front of and goes through the radiator and radiates radiates energy through the fins and cools down so it can go back around and remove more heat from your engine. So when you have two objects at different temperatures and you place them in contact with each other, we get heat flowing from the high temperature material to the low temperature, and it's going to keep going until they get to the same temperature. The amount of heat lost by the initially warm object is going to equal the amount of heat gained by the initially cold material. And this is the basis for a lab technique called calorimetry, which is what we're going to do today in lab. So if we think about a block of metal at 55 degrees Celsius added to water at 25 degrees Celsius. So I'm going to draw you pictures. They will not be pretty. So here's our beaker. And it's got water in it. And the water is 25 degrees Celsius. And then we put this piece of hot metal into the water. I don't know why that's three-dimensional when the other objects are not, but whatever. And that's 55 degrees Celsius. So there will be thermal energy transfer. There'll be energy transfer as heat from the hot piece of metal to the cold water. And the metal will cool down, and the water will warm up, and eventually their temperature will be the same. What's important is that all the energy lost from the metal goes into the water. And so we can say that the heat lost by the metal is equal to the heat gained by the water. Now, if you put the negative sign on the metal or the negative sign on the water, it doesn't matter. They are just opposite in sign. It's your point of view, right? If I give Jose $5 That's negative from my point of view and positive from his point of view. So if you take his point of view, that's a positive exchange. If you take mine, it's a negative exchange. That's all that is. Negative for one, positive for the other. Well, what does Q equal? Q is mc delta T. The mass times the specific heat capacity times the change in temperature. So this for the metal must equal and be opposite in sign to the mass of the water, the specific heat capacity of the water, and the change in temperature of the water. This allows us to measure the transfer of heat because we can measure the temperature change of the water with a thermometer. It's really easy to do. And from that, we can figure out things like what the specific heat capacity of the metal is. So let's do an example. A block of copper of unknown mass has an initial temperature of 65.4 degrees Celsius. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? Now my question is, why would you do this instead of just putting the copper block on a balance? Wouldn't that be easier? It would, but that's not what we're doing. Okay, these types of problems, pictures can be really helpful. Okay, so I'm going to draw, and see, you can draw pictures without being an artist. I'll make my copper kind of copper colored. So there's my copper down there. It looks like, well, here's one of my kids' favorite jokes. What's brown and sticky? A stick. But that looks like poop, doesn't it? It looks like poop. Reminiscent of the poop that got tracked all over my house. I'm going to go back to red because I just... No, well, let's see. Well, it's copper, though. We'll make it red. Okay. Yeah, but blood isn't square. There, it's red. So that was hot, and the other thing was cold. So I'm going to use colors to help me organize here as well. So we don't know the mass of the copper. We know the initial temperature of the copper, right? The initial temperature for the copper is 65.4 degrees Celsius. It's immersed in a beaker, and it's giving us the mass of water. So I'm going to write the mass of the water over here. Mass equals 95.7 grams. The water was at 22.7. That's the initial temperature for the water, 22.7. Oh, we'll just go into the beaker. The final temperature is 24.2. Which substance does that refer to? Both of them. The final temperature is the same for both of them. So for the water, the final temperature is 24.2. And for the copper, the final temperature is 24.2 degrees Celsius. Now, we wrote down all of our numbers, right? So now what we need to remember is that Q for the copper is equal to negative Q for the water. It really doesn't matter which one you put the negative sign on. One of them has a negative, the other does not. The heat gained by one is lost by the other. Oops. What does Q equal? MCAT, MC delta T. So over here we've got, no, not Q, M, the specific heat, and delta T. Now we don't want to lose our negative sign. And then over here, we've got M, C, delta T. The heat lost by one is gained by the other. What are we trying to find? We're trying to find the mass of what? The mass of the copper. So this is the guy we're looking for. That's not a good color. This is the guy right there. So what we can do is we can take this equation and rearrange it. And we're going to end up with the mass of the copper being equal to negative, what did I do? That's not what I meant to do. Negative the mass of the water times the specific heat capacity of the water times the change in temperature of the water. We're going to divide that by the specific heat capacity of the copper and the change in temperature of the copper. What's the change in temperature for the copper? It's final minus initial. So the final temperature was 24.2. Subtract the initial of 65.4, and that's negative 41.2. The negative means the temperature went down. One of these temperature changes should be positive and one should be negative. What's the temperature change for the water? It's also the final minus the initial. The final is 24.2, and subtract the initial, 22.7. This one ends up being positive, 1.5 degrees Celsius. We've got the mass of the water. We've got the delta T's. Where do we get CS? From the chart. What's the specific heat capacity of copper? 0.385? And what are the units on that? Is that joules? Joules per gram degrees Celsius. The specific heat capacity of water is 4.184. Joules per gram degrees Celsius. Now we can put all these numbers into the equation and solve for the mass. I'm going to do it way up at the top because I made a mess down there. So M equals, we need the mass of the water, 95.7 grams, times the specific heat capacity of the water, joules per gram degrees Celsius, times the change in temperature, which was 1.5 degrees Celsius. And that's all divided by the specific heat capacity of the copper, 0.385 joules per gram degrees Celsius, times the change in temperature for the copper. It's a negative number, negative 41.2 degrees Celsius. Those units cancel, these units cancel, and we end up with units of grams, which is awesome because that's a mass unit. So we have negative 95.7 times 4.184 times 1.5 divided by 0.385 divided by negative 41.2. And that comes out to be a positive number. If you get a negative number for your mass, you were messy with your signs. So how many sig figs should that have? What about this guy? 2. When we said this was a very small temperature change, and it was measured to the nearest tenth of a degree, but there were only 2 significant figures. So this can only have 2, and so we're going to end up with 38 grams as the mass. There are so many problems that can be done with this concept. Any questions? This part right here is really the key to the whole thing. Heat lost by one thing has to be heat gained by the other. And then you just elaborate on that. So that was talking about heat, about Q. And then there's work. Pressure volume work is one kind of work. It's work caused by a volume change against an external pressure. So when gases expand, the change in volume is positive, but the system is doing work on the surroundings. So the work is done by the gas, and so the work is negative. So here's an equation for pressure volume work. Work equals negative pressure times the change in volume. That's going to end up with some interesting units, isn't it? Pressure, if pressure is measured in atmospheres, then we're going to have atmospheres, and if volume's measured in liters, we're going to have atmospheres times liter. And how is that a unit of work? Well, this is the relationship we need. A joule, 101.3 joules, is equal to 1 atmosphere liter. Just because. So a cylinder equipped with a piston expands against an external pressure of 1.58 atmospheres if the initial volume is 0.485 liters and the final volume is 1.245 liters. How much work in joules is done? This is pressure volume work. Work equals minus P delta V. Delta V, delta is always final minus initial. The final volume minus the initial volume. The final volume is 1.245 liters. That was ugly. The initial volume is 0.485 liters. 1.245 minus 0.485. My calculator is showing me 0.76. Is that good? Sig figs. This number has 3 decimal places. We're subtracting here. This number has 3 decimal places. The difference has 3 decimal places. What do I put for the third one? A 0. My calculator doesn't understand. So that's the change in volume. So we have negative 1.58 atmospheres is the pressure times the change in volume, 0.760 liters. And that gives us negative 1.2008. And the units there are liter atmospheres. And that should have 3 sig figs. Does that answer the question? No, because the question wanted the answer in joules. So we need to convert that. So minus 1.2008 liter atmospheres. We need to convert this. There's 101.3 joules in 1 liter atmosphere. So we take that number times 101.3, and this will be our final answer. So now I'm going to round it off to 3 sig figs, 122 joules. That minus sign fell down. So we can say that W equals minus 122 joules. Sometimes Mastering Chemistry uses words instead of signs. So how much work is done by the gas? 122 joules.